Okay, guys. So last time in our last lecture on Wednesday, we were talking about continuity of functions. So we started on Monday, then continue on Wednesday, and we saw several theorems that allow us to decide whether a function is continuous or not. And the bottom line was that as long as you're given a function defined by a single formula, let me pull up the theorems here. If the function is not piecewise and is defined by a single formula, basically the continuity question boils down to a domain question. And let's see, go here. We can see that in here, because we have these nice properties that says that continuity behaves well with respect to all the arithmetic operations that we can do: addition, subtraction, multiplication, and division. And therefore, and all the functions that you know, polynomial, rational functions, radical functions, trigonometric, exponential, logarithmic, they are all continuous on their domain. Okay, so the continuity question boils down to just a domain question. And then to top this off, we also have this nice theorem that tells us, let's see, what is it right here, that says that if you look at the composition of two functions that are continuous, then this composition is continuous as well. Okay, so I actually want to make a remark on this because it was not written here, but it follows from this theorem. It's basically what the theorem is saying, but I didn't write it, which is the fact that a continuity means that if you have a continuous function and you take the limit of a continuous function, then you can pass the limit through the function, calculate the limit of what's inside, and then your answer will be the function evaluated at that limit. So let me just write it down so you will understand what I just said. In other words, if this function f is continuous, when you take the limit as x approaches a, okay, what you can do is you can pass the limit through the function, first compute the limit of g, whatever the answer is, which is g of a in this case, because g is continuous, then you evaluate that at the function f as a result of your limit. So for continuous function, you can pass limits through. And we did several examples last time in finding intervals where a function is continuous, and most of the time boil down to figuring out the domain. Only when you have piecewise functions, that's when you have to, be a little bit careful and then work more carefully. But and at that point, usually you have to focus on those points at which the function changes formulas, and then at that point you will need to use the definition of continuity at a point. Okay. Okay, so let me make the remark that I just mentioned about the limit of continuous functions, and then I would like to do more examples. And after that, the idea is I want to present to you a theorem that I kind of mentioned this theorem earlier, and also you saw it in pre-calculus. It's called the Intermediate Value Theorem, and this applies for continuous functions, and this is one of the most important theorems that we have in this chapter. Okay, so I'd like to explain this theorem, and we're going to do some examples, and this will be the stopping point for the exam. Okay, then you're going to do test 1 next week on Wednesday, and then on the lecture of Friday, when I do the recording, I will begin talking about derivatives. Okay, I don't want to introduce that now because anyways, I want you to focus for the exam. Okay, so before I get into more examples, let me do a remark here. So recall, if f and g are continuous, and in parentheses, g is continuous at x equals a and f at g of a, okay, then what we saw was that the composition f of g of x is also continuous at x equals a. But what this really means, or one thing that implies from here, is the fact, so that means that if I take the limit as x approaches a of f of g of x, right, Because it's continuous, that limit is going to exist and it's going to be equal to the value of this composition at A. Okay, let's dissect this a little bit more. So what is G of A? Well, remember, G is continuous at A. So that means that the value of G at A can be replaced by the limit. This right here is the same thing as limit as x approaches A of G of X. Let me write it down. So this is f of the limit as x approaches A of G of X. So let us ignore the term in the middle between these two equal signs for a second and look at the left side and the rightmost side. What just happened? We're taking the limit here, okay, of a composition, and we know that the outside function is continuous, the f function is continuous. And what happened? The limit went inside the function, and then we actually took the limit of g first, and then the result is f evaluated at that value. Okay, so that's the remark. In other words, if f is continuous, it's a continuous function, then if you take the limit as x approaches a of f of g of x, you can pass the limit through. So compute the limit of whatever is inside in the argument of f, and then the result that you get, you evaluate f at that number, and that's the answer. That's the result of the limit. Okay, so it's just a little observation, and the continuity of f is the one that allows you to do this. Okay, the fact that it's continuous. Okay, so all right, I just wanted to make this parenthesis and mention this. So now let's go back and let's do more examples. Okay, so more examples. Okay. Um, okay, actually, let me do an example of this little property that I just mentioned here, just to so that you can see how this can be applied nicely. So, for example, evaluate the limit. So find the limit, and this limit is going to be limit as x approaches 0 of 1 plus 1 over, let's say 1 plus 3x to the 5 over x. Let's make it simple. To the 5 over x. Okay, so let's try to compute this limit. If you remember, this limit resembles something. So, and let's say x is approaching 0 from the right. So if you remember this limit resembles something that one of the special limits that we learned some time ago. So recall, we have the special limit that limit as x approaches 0 from the right of 1 plus x to the 1 over x. This limit equals e. This is actually the definition of e. Okay, and hopefully by looking at this problem that I just wrote, this kind of limit should come to your mind, because notice that this actually has sort of the same form. Notice that if you try to evaluate this, the original limit, we're going to have 1 to the infinity. And remember, this is an indeterminate form. Okay, so we need to do something about this limit, and hopefully, once again, the special limit 1 plus x to the 1 over x as x approaches 0 from the right comes to your mind, and this limit is e. So we would like to somehow modify the original limit in such a way that we can bring this expression that gives us e into the mix. Okay, and the idea is that I'm going to use a substitution. Okay, I'm going to change variables, and this is going to allow us to be able to do what we need. Okay, So for example, the moral of the story here is that the same thing that is here, okay, has to be down here. Okay, that's the idea. Okay, so because I have a 3x, okay, so I have a 3x in the original problem, that means that I would like to have a 3x under the 5 as a denominator. Okay, because that 5 is not really an issue, because we can do the following. I could do, for example, 1 plus 3x to the 5 over x. I can rewrite this as 1 plus 3x to the 1 over x, and then all of that raise it to the 5th power. Remember, when you do the exponent of an exponent, you multiply. So these two expressions are equal to each other. So, that 5 is not really a problem. The issue is that I have a 3x here, and I have an x in here. So I would like to have the same thing. We have two choices. We can force the 3 to show up by multiplying top and bottom by 3, the fraction 1 over x, and then the 3 in the top, we pull it in the other exponent as we did with the 5, and then we have what we wanted. Or we can do a change of variables. Okay, we change variables, then we will have the original limit that we have written in red here, and I'm gonna do that. Why? To give you more practice in changing variables. Okay, so instead of following this route of modifying the actual expression that I have, I'm gonna change variables to make it easier. So we will change variables, and that way you see another example in which change of variables is helpful. Okay, so instead of 3x, I just want to have one variable there. So I'm going to call 3x, I'm going to call it t. All right, so let t be equals to 3x. Now that means that in the limit, everything that has an x has to become t. Okay, so that means that x itself is going to be t over 3. Okay, and also I need to say something about t. When x approaches 0, what does t approaches to? Okay, now this is it's clear that t also approaches 0, right? Also, limit as x approaches 0 from the right of t is the limit as x approaches 0 from the right of 3x, because t equals 3x, which is also 0. Okay, and moreover, notice that if x approaches 0 from the right, then this limit is going to be equal to 0, but with positive numbers. Okay, so because here we have a positive quantity. So when x approaches 0 from the right, t approaches 0 from the right as well. So we are ready to make our substitution. So limit as x approaches 0 from the right of our original problem. I'm going to make a substitution. So instead of x approaching 0, we have t approaches 0 now. Okay, as we figured out. And also here we're going to have 1 plus, now instead of 3x, I'm going to put a t, because t equals 3x. And then 5 over x. Okay, this would be 5 over, and instead of x, I'm going to put t over 3. Now, as you know, this is the same thing as 15 over t, because the 3 comes up. So this is the same thing as the limit as t approaches 0 of 1 plus t to the 15 over t. And the only thing that I'm missing now to make this limit the same as the red limit from the top, the property that we use to define E, is to, get rid of this 15. And we can do that by using the remark in the top line, that I can use the properties of exponent. So now we can write this as limit as t approaches 0 from the right of 1 plus t to the 1 over t, and all of this, we raise it to the 15. Okay? So the change of variables did this to us. Now, the question is, how do we evaluate this limit? Well, let's now use the discussion that we had here about composition of functions. Okay, notice that here we have a composition. What's the composition that we have? So right here, there is a composition taking place. what's the outside function? So the composition, I'm gonna call it f of g of t. In this case, the outside function f of t is the function, the power function t to the 15, and the inside function is what we have inside the parentheses, or the bracket in this case, right? If I plug in g inside f, then we get exactly the expression that we're finding the limit of. So hopefully you realize this. And notice that the outside function, which is t to the 15, is continuous. This is a power function. So this one right here, this is a continuous function. And as we discussed above, when the outside function is continuous and you find the limit of a composition, you can pass the limit through. So by continuity, this is the same thing as, so I'm going to pass the limit through, the limit as t approaches 0 from the right. So, typically we don't write this step, we just do it, but I'm going to write it so you see it. So, we pass the limit into the power function, take the limit of whatever is inside, and then the result is that limit raised to the power 15 in this case. Okay? So here we use the continuity property that we discussed above. Now, this right here is exactly our special limit, right? So we know that this equals E. So now the answer to the problem would be E to the 15. Okay, so in this example, we saw two things. We practice changing variables once again to make our limit easier. And second, it was an application of this property that when you have the limit of a composition and the outside function is continuous, you can pass the limit inside the function, pass it through the function. Okay. All right. Okay, so just wanted to point that out. Now let's do more examples with piecewise functions. So additional examples. Additional examples. And the problem would be find A or B. So find the constants. Let me say find the constants for the value of the unknown constant. Find the value or values. Oh, just one back. The value of the unknown constant. The unknown constants. It could be more than one. And so that make the function continuous everywhere. In other words, I'm going to give you a function, and this function is going to have an unknown constant, at least one, in it. And our job is to figure out what should that constant be so that the function is continuous everywhere. We want the function to be continuous for at every real number. Okay. All right. So we're gonna do several examples. Let me write the first one. So we have f of x. Actually, I'm gonna write them all. As you watch this, since you're watching this video now, what I would like to suggest to you, you already know how to do this, and you have been doing this in the homework, several times. I'm gonna write out the problems. Just pause the video and try these problems yourself, and then keep watching and see whether you did it correctly or not. Okay, so let me write down all the problems that I have in mind, and then we're gonna go to the solution. Okay, so this is 2, provided that x is less than or equal than -1. Then is ax plus b. So here now a and b are unknown, provided that x is between -1 and 3. Then let's make it -2, provided that x is greater than or equal than 3. Okay, the other one will be g of x equals 4 times sine of x over x, provided that x is less than 0, then a minus 2x for x greater than or equal than 0. And the last one is going to be 2 times e to the ax minus 2, provided that x is less than or equal than 4, and then ln of x minus 3 plus x squared, provided that x is greater than. So once again, here we have 4 functions, okay, and these are piecewise, and notice that these functions, they have unknowns. In this case, I'm using the letters a and b to denote the unknowns. So problem b is the only one that has 2 unknowns, a and b, but they are constants. Okay, our job is to figure out what these constants have to be so that these functions are continuous everywhere, okay, for every real number. In particular, we want to make sure that they are continuous at those points at which they change formula. Okay, so go ahead, pause this video, and then give it a try. Try to solve these problems on your own, and then come back and watch their solutions. Okay, so let's go. So solution. So first one is f of x equals x cubed, x less than or equal than 2, and then a x squared, or x greater than 2. And our job is to give a value for a. So we want to figure out what should this guy be so that this function is continuous everywhere. Now, uh, certainly uh, we need to split this into 3 cases as we saw last time, right? So we have 3 cases. So we have the case when x is less than 2, the case when x is bigger than 2, and then the case when x is equal to 2 is special because that's the point at which the function changes formula, right? Less than 2 because in this case our function is just the function x cubed, right? And in the other case our function is the function a times x squared. And because the function changes formula around 2, then we need to consider what happens at 2 as well individually. Now, in the first situation, when x is less than 2, the function is the cubic function x cubed. And as you know, this is a power function. Power functions are continuous. So it's continuous on the interval from negative infinity to 2. No issues there. When x is bigger than 2, we have a parabola. Once again, continuous. So regardless of what a is, I don't care. A is a constant, okay? It's a parabola. It's not going to affect the continuity. So it's continuous as well. So our function is going to be continuous from 2 to infinity. The only question that remains is, what about at x equal 2? Now, because this is a point, we need to use continuity at a point. And for that, there are 3 things that we have to check, okay? The first one is the function defined? So can we plug in 2 into the function? Well, can we plug in 2? Yes, we can. In this case, we need to use the first formula, right? So that means f of 2 equals 2 cubed, which is 8. So condition number 1 satisfied. Condition number 2, the limit. Does the limit exist? Limit as x approaches 2 of f of x. Does this limit exist? All right, so to be able to answer this question, we need to see if we can compute the limit. And because this function breaks, is piecewise and changes formula around 2, to be able to compute this limit, we need to know what formula to use. And in order to be able to do that, we need to look at side limits. because we need to know whether we are to the left or to the right of 2, whether x is less than 2 or bigger than 2, so that we can pick the correct formula. So we're going to look at side limits for this. So we're going to go from the left, and then we're going to take the limit from the right, and then we see what happens. So okay, so from the left, this means, remember, that x is less than 2, and therefore we should be using the first formula, which is x cubed. So as limit as x approaches 2 from the left of the function x cubed, and this is 2 cubed, which is 8. Okay, all right. Now from the right, this means that x is bigger than 2, so we should be using the second formula. So as limit as x approaches 2 from the right of 8 times x squared. So this time, this is going to be equal to 8 times 4. So, whatever a is, times 4. Or 4a. Let me write it as 4a. Okay, so we have our left limit, we have our right limit. Now remember, we want to answer yes to question number 2. Why? Because we want continuity everywhere. We want the function to be continuous. Now, as you know, to be able to say yes in question number 2, we have to make sure that the side limits agree, because if the side limits are different, then the actual limit as x approaches 2 does not exist. And, A is the one that will tell you whether these two values will agree or not. In other words, if we want to answer yes to the question that the limit exists, but then we need to make sure that whatever left limit we obtain, it has to match the right limit that we obtain. In other words, 8 better be equal to 4 times a. Okay, and this here is a very simple little equation, and it follows then that the constant a has to be 2, right? 8 divided by 4. In other words, what's the answer to question number 2? Does the limit exist? Yes, as long as, so there's a big if here, if a equals 2. Because if a is different than 2, if a is something else, then the right limit is not going to match the left limit, and therefore we are not going to have continuity. We're going to have a gap in the function. There will be a jump discontinuity, non-removal. Okay, so that's how we found our condition. Now it's just a formality, step number 3, but indeed, because when a is equal to 2, the two limits agree, and they're actually equal to 8, which is the value of the function, so we're good. So limit as x approaches 2 of the function is going to be equal to 8, provided that a, the constant a equals 2, which happens to be the value of the function. So we're good there. Okay, so moral of the story. So the final answer is, remember, the question is find the constant that will make the function continuous everywhere. So the final answer is, okay, a equals 2. Okay, so as a solution for the first one, let's do the next one, the one that has two unknowns. So part B, let's do f of x equals 2 as long as x is less than or equal than -1, and ax plus b, x between -1 and 3, and then -2 for x greater than or equal than 3. Okay, so we want to make sure this function is continuous everywhere. So naturally, there are several cases that we need to consider, right? So in fact, there are 3 cases plus 2 more. Okay, so 5 cases in total. Why 5 cases? Well, we have a case for each piece, right? And then a case for each of the points at which the function changes formula. And this happens at 2 points. The function changes formulas for the first time around -1, and then it changes once again around 3. So those two cases have to be analyzed separately. So the cases are x less than -1 and x between -1 and 3, then x bigger than 3, and then we have to analyze x equals -1 individually, and we also need to analyze x equals 3 individually. Okay, so these cases need to be analyzed. Now the first three are really, just because when you look at the formulas, the way that you can do this quick is just take a look at the formulas of the function and make sure that the domain is okay. The interval that corresponds to those formulas is part of the domain of that formula, and then it will be continuous there. For example, when x is less than -1, our function is just the function 2, f of x equals 2. This function is continuous everywhere, so in particular continuous, so nothing to worry about. Between -1 and 3, the formula is ax plus b. That's a line. I don't know what is a, I don't know what is b, but this is a line. A is the slope and b is the y-intercept. So it's a line, and lines are continuous. So regardless of what a and b are, this piece is continuous on its own. And when x is bigger than 3, we have the function -2. Once again, continuous everywhere, in particular, is continuous for x bigger than 3. So, typically the pieces themselves are not the issue. The issue is, the issues are found at the points at which the function changes formulas. That's where you need to concentrate your attention, really. All right, so let's see -1. What's going on around -1? So just to give you an idea of, what happens in this type of problems. Here now we have two unknowns, okay? So what's going to happen is that, we have 2 points left to discuss. So around -1, when we analyze -1, you're going to see we're going to get one equation that relates A and B, okay? Because we want to enforce continuity at -1. So this is going to force us to come up with an equation containing A and B. Same way that in the previous problem, we had this equation in terms of A. Now, because we have two unknowns, we're going to have an equation in terms of A and B. And then, when you look at this, the second case, x equals 3, that's going to give us another equation relating A and B. So then we're going to have a system. We're going to have two equations with two unknowns. You solve the system. Okay? And that's the idea. All right, so let's do it. So I'm going to do x equals -1 in red, x equals 3. Let's do it in blue. Again, because this is a point, we need to go with the 3 steps. Okay, first, what's the value of the function on -1? Can we evaluate it? Yes, we can. The first piece we use, and that's equal to 2. Okay. Okay, for the second one, the limit as x approaches -1 of the function. Does this limit exist? All right, so if we want to answer this question, again, because it changes formula, we need to look at side limits. So left limit, right limit. Okay, left limit, remember, that means x is less than -1. So we are looking at the first formula, f of x equal 2. So that's a constant 2, and the limit of a constant is a constant. So that's 2. Now the right limit, this means x is bigger than -1. So we use the formula in the middle, ax plus b. But remember, we're close to -1, so we are in the formula of the bin, in the middle. And we don't know what a and b are, but this limit is about x. So just plug in, and so we're gonna get -a plus b, or just b minus a. Okay, because we're plugging in -1. Okay, so now because we want the limit to exist, then we need to say, okay, we better have these two quantities equal to each other. So we get the equation that 2 equals b minus a. Okay. All right. So let's see. So we get this relation, and by the way, notice that so our answer is yes, the limit exists, and our if is if b minus a equals 2. That's our condition. And by the way, because one of the side limits is actually a number is equal to 2, notice that when this happens, when b minus a equals 2, then the limit will exist, it will equal 2, which is the value of the function. So condition number 3 is actually, satisfied as well. So I'm going to say here condition number 2 plus condition number 3. They are done at once because the answer is yes, and the limit equals 2, which is the value of the function. Okay. All right. So I got one equation. Let's call this equation number 1, or let me start this equation. This is equation star. Now let's repeat the process with the other point. Notice that there are, at this point, there are infinitely many numbers, infinitely many values for b and a that we made this work. Okay. So this is not enough. For example, b could be 4 and a could be 2. B could be 20 and A could be 18, and so on, right? So there are infinitely many possibilities here. So we need to find which one is the one that works, that we make the function continuous everywhere, because those will guarantee continuity at -1, but not necessarily at 3. Okay, because this is a point. Now we go through the steps. First, can we evaluate the function at 3? Let's see. Yes, we should use the third piece. So in this case is -2. Because when x is equal to 3, we are in the third formula. So second, the limit question. What can we say about the limit as x approaches 3? That this limit exists. Once again, side limits. So limit as x approaches 3 from the left. Limit as x approaches 3 from the right. Okay, so from the left, x is less than 3, so we're in the second formula, and that's ax plus b. So that's limit as x approaches 3 from the left of ax plus b. And so this limit will be 3a plus b. Plugging in x equal 3 into x. And then when x approaches 3 from the right, that means x is bigger than 3, so we should be looking at the last formula, which is the constant -2. So limit x approaches 3 from the right of the constant -2. So this is -2. So as before, we want these two limits to match so we can ensure continuity. So we need to force the two limits to be equal to each other. So we get another equation. We get that 3a plus b better be -2. Okay, let's call this equation double star. So the answer to number 2 is yes, as long as we have the equation 3a plus b equals -2 satisfied. Okay. And notice that in that case, the value of the limit then would be -2, because that's one of the side limits. And when they match, then that's the actual value of the limit, which coincides with the value of the function. So we also ensure that condition 3 is satisfied. Okay. All right. So we want continuity everywhere. We know that the function is continuous everywhere, except perhaps at -1 and 3. And the continuity at these points will depend on where a and b are. To ensure continuity at -1, we need to satisfy equation star 2 equals b minus a. And to ensure continuity at 3, we need to satisfy equation double star 3a plus b equals -2. So if we want to have continuity simultaneously at both -1 and 3, we need to simultaneously satisfy these two equations. In other words, we get the system that, okay, let me put a first, that -a plus b equals 2, and then 3a plus b equals -2, right? So we get this system. So again, the first one is equation star, and the second equation is equation double star. Okay, I just rewrote b minus a. I wrote it as -a plus b, just to have the a's first and then the b's. Okay. All right, now we solve this system, and you can solve this however you want. You can use the substitution method, or you can use the addition method. It's up to you. Okay. I don't know. I'm just gonna use the substitution method. So, for example, here in the first equation, we get that b is gonna be equal. I'm gonna solve for b. B is gonna be equal to 2 plus a. Okay. And that means that then I can plug this into the second equation, and then it tells me that 3a plus 2 plus a, which is b, is going to be negative 2, and now we solve for a. So that would be 4a equals negative 4, so a is negative 1. And once you have a, then we can easily find b, because b equals 2 plus a, so that means that b is going to be equal to 2 minus 1, so b equals 1. And let's make sure that this solution satisfies both equations, equation star. So let's see, b is equal to 1, a negative 1, so 1 minus 1. So 1 minus 1 is 1 plus 1, which is 2. So equation star is good. And then when we plot these values into equation double star, we get negative 3, because 3 times negative 1. So negative 3 plus 1, that's negative 2. So we're good. Okay. So you know, the answer to the question is, in this case, our job is to figure out what a and b are equal to, so that the function f is continuous everywhere. Well, a must be negative 1 and b must be positive 1. Okay, that's the solution to that problem. Okay, so with this, and then the others is exactly the same thing. So the others, I'm gonna do them a little bit more quicker. Let's see, C, we have the function g of x. I think we call it g. Let me just double check. Yeah, so we call it g. And is given by 4 sine of x over x for x less than 0, and then a minus 2x for x greater than or equal than 0. Okay, so again, the first two cases is just a formality, less than 0, greater than 0, and then we're going to concentrate what happens at x equals 0. So when x is less than 0, our function is 4 sine of x over x, and this will be continuous on its domain, because it's a quotient of two continuous functions, and as long as the bottom is not 0, we are good. And in this case, x is less than 0, so we are okay. So this is continuous. When x is greater than 0, we have a line. And once again, lines are continuous. It's a polynomial. So if to be able to figure out the constant a, now we need to look at what happens at the point x equals 0. And of course, this is the point that, could potentially create issues, because it's where the function changes formula. This is where a gap may show up. Okay. All right. So we have to look at the three conditions. So the first one was the value of the function at 0. In this case, we need to use the second piece, right? And so that would be a minus 2 times 0, which is just a. Okay, so let's satisfy. Second, the limit. We need to say something about the limit as, does this limit exist? The limit as x approaches 0 of the function. And the function is g. That this limit exists. All right, so because it's piecewise and it breaks around 0, then we need to look at side limits. So from the left and the limit from the right. So for the left limit, remember x is less than 0, and in that case, we need to use the first formula, which is 4 times sine of x over x. And if you remember, sine of x over x is one of our special limits, and that limit equals 1. So this will be 4 times 1. So this one right here is 1. 4 times 1, which is 4. And then for the other limit, the right limit, this means that x is bigger than 0 because we are approaching 0 from the right. So we should use the second formula, a minus 2x. And so in this case, we're going to get a for the limit. And because we want continuity, we want to make sure that we answer yes. And if we want to answer yes, then we better have that 4 equals a, or a equals to 4. So does the limit exist? Yes, as long as a is 4. And notice that in this case, if a is 4, then that means that we made the value of the limit 4, and then the value of the function is also 4 because it matches a. Okay, so we basically did 2 plus 3 here together. Okay, and that's our answer. A equals 4. Okay. All right, so I will see, and then let's take a look at the last one. So we have f of x equals 2 times e to the ax minus 2. I don't remember if I put the 2 on top or in the bottom. Okay, good. This is as long as x is less than or equal than 4. And then let's do ln of x minus 3 plus x squared as long as x is greater than 4. Okay, so again, same thing. In this case, we have 3 cases. So less than 4, greater than 4, and then x equals 4 is special because that's the point at which the function changes formula. So when x is less than 4, our function is 2 times e to the ax minus 2. So remember, our job is to figure out this a. Okay. And what do we know about this function? Well, this is the difference of two functions. The first one is an exponential function, which is continuous everywhere. In particular, it's continuous for x less than 4. And the second function is a constant, the function 2. And the difference of continuous is continuous. So, continuous. You see, those theorems are very handy. They allow us to deduce continuity without having to basically do much work. Okay. All right, so when x is bigger than 4, we need to be looking at the second formula. And here we have to be a little bit careful because remember, the natural log function, has some restrictions. For example, you cannot do ln of something negative, but the stuff in the argument of ln here is x minus 3. That's the term that we have in the argument. And we just need that to be greater than 0. And this happens whenever x is bigger than 3. But we're looking at this formula when x is greater than 4. So we're good. So this is continuous on its domain. In particular, the first piece is continuous. The second piece is continuous, x squared. The sum of two continuous functions is continuous. So this is continuous on the interval 4 to infinity. So we're good. This one is continuous on negative infinity to 4. So once again, here a can be whatever so far, because this doesn't affect the continuity of the two pieces. The question is, what about the connecting point? When x is 4, what should a be so that the two pieces connect nicely and, to ensure continuity? We want to make sure that we don't have any gap. Okay, so, the basic things. First of all, can we plug in 4 into the function? Yes, we can. We can plug into the first one, the first piece. This is to make sure that we don't have any hole. And so we get 2 times e to the 4a minus 2. Okay, so that's what we get. Now, second, the limit. What's the limit as x approaches 4 of the function? Does this limit exist? And, side limits are in order here. Look at the left limit, and then we're going to look at the right limit. Okay, so left limit, that means x is less than 4, so we should be using the first piece for this. And so we're going to get 2 times e to the 4a minus 2. That's what we get the first for the left limit. Now let's do the right limit. What's going on? Okay, so for the right limit, because x is approaching 4 from the right, that means x is bigger than 4. So we need to use the second formula. So that would be ln of x minus 3 plus x squared. And when we plug in, we're going to get ln of 1 plus 16. But remember, ln of 1 is 0. So we get 16. Okay, so now because we want equality, then we need to make sure that the two limits match. So from here we get the equation that 2 times e to the 4a minus 2 better be equal to 16. Okay, so now let's go ahead and let's solve this equation to figure out what a has to be. So 2 times e to the 4a minus 2 equals 16. Okay, so I'm just gonna, okay, let's see. So when we add 2, we get 18. That means 2e to the 4a equals 18. So e to the 4a equals 9, dividing by 2. And now here, if we want to solve for a, we need to rewrite this as a logarithm. So remember, every exponential expression has a logarithmic counterpart. Okay, so in this case, it is ln. So this means that the exponent, which is 4a, right here, so 4a is going to be equal to ln of 9. Okay, and then a equals ln of 9 over 4. Let's simplify this a little bit more. Ln of 9, we can write it as 3 squared. So 9 is 3 squared. Now by using properties of ln, these 2, we can bring it to the front. We can bring it here. So it becomes 2 ln of 3 over 4. And then these 2 cancel with the 4. And so we get ln of 3 divided by 2. Okay, so that's our value of a. So when a equals ln of 3 divided by 2, the two limits are going to match. So the answer is yes. It's a big if a equals ln of 3 over 2. Okay, and then in that case, the value of the limit is going to be 16, which will exactly be the value of the function, because that value for a is the one that we made the expression 2e to the 4a minus 2 equals 16. Okay, so we basically, with that value for a, we verify 2 and 3, and the answer is that number we made the function continuous. Okay, so now you can see whether you arrive to these values or not when you try these problems on your own. Okay, so I just wanted to do these examples to make sure that you have plenty of examples for continuity. The homework has a lot of problems related to this, in which you have piecewise functions. Like most of the homework problems are like this. You have piecewise functions, and then you need to find the constant that makes the function continuous. Okay, so the last thing that I wanted to talk about was about this theorem called the Intermediate Value Theorem. This is a very important theorem in mathematics, and this chapter, I would say, is among the most important ones. And because actually it's the first theorem that will, it's a theorem that allows to find solutions of equations whenever an equation involves continuous functions. And this is essentially what mathematics is about, being able to find solutions to equations. And even though it may sound, I don't want to say what mathematics is about, but it's the motivation, the root of why people care about mathematics is because eventually things translate into an equation and then you want to solve that equation. Then, what techniques do you use for that? So intermediate value theorem allows to make sure that we can always solve equations involving continuous expression, at least numerically. Okay, so when you put an equation in a computer will spell out a solution for you or an approximation to a solution. How is this done? Well, this is done using more advanced techniques because they are faster, etc. But at least it can be done using an application of the intermediate value theorem. So that's why it's very important. It guarantees that we can find solutions. Okay, so let me just say what it is. It's actually a very straightforward statement, but it's surprisingly hard to prove. In fact, we don't have the knowledge nor the tools at this level, in this course, to be able to prove this statement, even though it would be very simple to understand, hopefully, like to accept what the statement says, to actually argue it and prove it formally is beyond the scope of this course. Okay. But let me explain what this is. So uh, let f, so the condition is let f be a continuous function. So f is continuous. So we have, okay, let me first do it informally and then we're going to write it formally. So f is a continuous function on a closed interval AB. So it has to be continuous in the closed interval, and what happens outside of this closed interval is not our concern. Let's just require that the value of the function at A is not the same as the value of the function at B. Just to make sure that we're not talking about the constant function. I don't want to look at horizontal now. So how will a potential picture of this function look like? So let me put here x and y, and so the picture looks nice. Let's put the function positive, but it doesn't have to be positive. Okay, it doesn't have to be above the x-axis. Let's say A somewhere over here and B somewhere over here. I don't know, let's say f of A is here. So that's the value of the function at A. And let's say that f of B, somewhere in here. Once again, doesn't have to be, it could be decreasing instead of increasing. But let's say that that's the value of the function. Okay, so this is what we have so far. And I know that f of A and f of B, they are not at the same level on the same horizontal line. They don't have the same y value because I'm requiring that those values are different. Now, if the function is continuous on the closed interval AB, what does that mean? First of all, it means that it has to be defined at every point between A and B. So when you look at the graph of the function in the closed interval AB, these 2 points that I just draw, they have to be joined, right? And as you know, we need to draw this nicely. In other words, we have to be able to join these points with a graph that can be drawn without lifting your pencil. So nothing weird happening. No holes, no gaps. There cannot be any breaks in the graph. No asymptote going to infinity, nothing like that. So I don't know, a potential picture is something like that. Okay? And you can draw whatever you want, but make sure that it's something that represents a function, passes the vertical line test, but it has to be continuous, so without lifting your pencil. And what does this mean? This is because the function is continuous. And what does this mean? Well, actually, here is a statement. Suppose now that I pick any point that I want between the two y values, f of A and f of B. Let's call it k. So I don't know, I'm going to pick a k in here. And basically, what the theorem says is that for any number k between f of A and f of B, I will always be able to find a number c that is between A and B, so that when I evaluate the function at C, I get K. It's a pretty straightforward statement, right? So for So then the statement says, with this condition, it says that for any k that is between f of a and f of b, there is a c that is between a and b, okay? There is a c that is between a and b, such that when I do f of c, I get k. In other words, every y value between f of a and f of b has a preimage, okay? There is an input between a and b, has a preimage between a and b. There is an input between a and b that gives me as an output that particular k that we just picked or selected between f of a and f of b. That's what the intermediate value theorem says, okay? Hopefully it makes sense to you and it's a straightforward statement, okay? Once again, to prove this is a different story. So we're not gonna get into this. Okay, so this right here is what we call the intermediate value theorem. Okay, so this is called intermediate value theorem. And I'm gonna abbreviate it by IVT. So let me write it. So theorem. I'm gonna write it formally, okay? But it's essentially what I just did above. So you just have to make sure that your function is continuous on the closed interval AB, and that the value of the function at A matches the value of the function, is not equal to the value of the function at B. That's it. After that, then this statement follows. Okay, so if f is a continuous function, on the closed interval AB, f of A is different than f of B, and k is any number between f of A and f of B. Notice that here I'm not putting inequalities because, it could be that f of A is less than f of B, as in the picture above, but it could be the other way around. Your graph could be going down, like f of A is bigger than f of B, okay? So that's why I don't want to put inequalities and just say k is between these two numbers, okay? Then there is a least, and I say a least because notice that if you look at this picture, there is another one, another C that will work, right? If we keep going, there will be another C here that will do the job. But the point is that there is at least one, okay? If there is more than one, that's fine. Point is that there is at least one. I don't want to erase the picture. So let's see. How far can I do? Oh, good. Then there is at least one C. There is at least one number C inside the interval AB, so as a C between A and B, okay? Such that when I plug in C into the function, we get that number K that we picked, okay? So in other words, every value between f of A and f of B has a preimage, okay? So that's has a preimage inside the interval AB. So that's the statement of the intermediate value theorem. In particular, and this is normally how this statement is used. So in particular, let me say here, corollary, this is special case. So special case. Assume further, so again, what are the conditions? F continues on AB, okay, F is a continuous function on AB, And then now what I want to say is, of course, f of a different than f of b, but now let's be a little bit more particular about this. Let's say that they have different sign. Now, it doesn't have to be that f of a is positive and f of b is negative. It could be the other way around. Okay? So let's say that they're different, but they have different sign. It could be that one of them is positive and the other one must be negative. So f continues on AB, f of a different than f of b, and this is the new condition that I'm imposing now in this special case. Let's say that f of a and f of b have different signs. Okay? Have different signs. Then, what can we conclude? So what can we conclude? Well, let's see. Let me put here. So we're gonna prove it, okay? But the proof is very simple. Let's draw a picture so you can see what it is. And then once I write down the proof, actually I'm gonna draw the pictures here, and then the proof is just one line. So let me show you two situations. So let's say here is A, here is B. There are two situations because it could be that one of them is positive and the other one is negative. Okay, so and there are two possibilities for this. So let's say f of a is positive and then f of b is negative. Okay, and then the other way around, let's say f of a is negative and f of b is the one that's positive. The point is that they have different sign. Now, because the function is continuous, what's going to happen? When we actually join the dots, right, notice what's going to happen. Point is that we are forced to cross the x-axis at some point. You see, like continuity, if you if you join the dots, you have to cross the x-axis at some point between a and b, and that's basically what I want to say. Now when this happens, if you have a continuous function and the function on a closed interval and the function changes sign at the endpoints of the interval, so at one point is positive, at the other point is negative, then the function has to have a zero inside that interval. So then f has a zero in the interval AB. In other words, there is a C between A and B. Actually, strictly cannot be equal because the function is not zero and at the endpoints is have different sign, one positive, one negative. So there is a C between A and B with f of C equals 0. Okay, so this is a particular case of the intermediate value theorem. The proof you can see basically here in this picture, but just to be formal, if you want to prove this, just say, okay, since f of a and f of b have different sign, since they have different signs, that means one is positive, the other one is negative. I don't know which one is it, so that's why let's say f of a is a positive and f of b is a negative. Okay, then uh, among the numbers in between, right? Remember k in the original statement, k can be whatever you want, right? In particular, 0 is between those two, right? They have different signs. Then uh, k equals 0 is between no, I think that's how we spell between. Now I'm not sure. 1t. Okay. So then k equals 0 is between f of a and f of b, and so by the intermediate value theorem, there is a C in the interval AB. What just happened here? And so there is a C. Come on. Oh, picking F of B. And so by the intermediate value theorem, there is a C in the interval AB such that f of C equals that K, and the K is 0, right? That's our proof. So basically what we're saying is, if you have a continuous function on a closed interval and the function changes sign at the endpoints of the interval, then there has to be a 0 in between the endpoints of the interval. So there is a point at which there is a value at which the function equals 0. And this is actually a statement about finding a solution of an equation, because as you know, every equation can be written as something equals to 0. Just move everything to one side. Whatever equation you have, just move everything to one side, and then you have 0 on the other. So the question is, will the function that you have, let's say on the left side, equal 0? Will that equation have a solution? Here we are saying that there will be a solution if you know that the function is continuous and changes sign around the endpoints of the interval. Then you will be able to find a solution. This statement does not tell us how to find it. So keep that in mind. This is an existence theorem. This theorem tells you that you can find the solution. There exists a solution between A and B, and it gives you an idea of where this is, because it gives you an interval and it's inside that interval. But it doesn't tell you exactly what the solution is. You still have to find it. Okay? I'm gonna show you in the examples one way to actually approximate the solution with as much accuracy as you want. And that's the best that we can do with this theorem. Okay, and we know that there is a solution. Now if you want to know what it is, what we can do is we can approximate it with whatever accuracy we desire. Okay, in a numerical way, and I'll show you how to do that. And that's the remarkable application that this theorem has. Okay, so again, the only conditions needed here is that when you want to use this theorem, you have to make sure that the function is continuous on the closed interval AB. Okay, and if you want to use this special case of finding a 0 or a solution to an equation, then you need the extra hypothesis that the value of the function at the endpoint must have different signs. Okay, if that's satisfied, then good to go. All right, so let's see examples. I want to do 2 examples. All right, so the first one will be show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0, 1. So before we discuss the solution to this, let me just make an observation here. Note, this question is equivalent to the following question. So we could have asked the question in the following way. It's equivalent to the following. Solve x cubed plus 2x minus 1 equals 0. Okay? So, I could have just given you this polynomial, this degree 3 polynomial, and asked you to solve this equation. And the point is that, this is not an easy job to do. Okay? So, but what we can do is make sure that at least we have a solution, and then we can get whatever approximation we want to that solution. Okay? So that's why I'm saying that theorem is helpful when it comes to solving equations. Okay? So let's see this in action. So show that the polynomial function has a 0 in the interval 0, 1. And then I would say here, approximate it, let's say, to 2 decimal places. So let's make sure that we give it with a 2 decimal place accuracy. Okay, so how do we do this? Okay, so first let's make sure that we understand that there is a solution between 0 and 1. So the first thing that we need to do is we want to use intermediate value theorem. And for that, we need to make sure that our function is continuous on the closed interval 0, 1. And certainly it is because it's a polynomial. So let's just write that statement. So solution. Okay, so we have the polynomial f of x, which is x cubed plus 2x minus 1. Well, we can say, okay, this guy, so let me say point number 1, this is continuous on the interval 0, 1, since it is a polynomial. And polynomial functions are continuous everywhere. Okay, now this is not enough to be able to use. So here, by the way, we need to use the special case of the intermediate value theorem, right? Which is the one that requires the value of the function to have different sign. And for the intermediate value theorem itself, you have to make sure that the values are different at their points. So first condition is satisfied, the function is continuous. Second condition, we need to see what happens to the value of the functions at the endpoint. Okay, the value of the function at 0 is -1, right? And the value of the function at 1 is 2. So at 0 is negative, at 2 is positive. So that means that the value of the function at the endpoints have different signs. So the conditions of the intermediate value theorem are satisfied. So now we can deduce that there must be a number between 0 and 1 that we give that when plugging into a function we get 0. So hence, by the intermediate value theorem, there is a C between 0 and 1 such that f of c equals 0. Okay? Because the function is continuous on the interval 0, 1 and it changes sign around these points. Now our job, so this finishes the question. We just show that this function has a 0 in that interval. It's just a matter of making sure that the intermediate value theorem can be used, that the conditions are satisfied, and then they're good to go. So we know there is a 0, but another question is, okay, let's find it. I'd like to know where is it, okay? Because who is this guy? What is this 0? Okay, so to find this 0, I'm gonna tell you what is the idea. Okay, so we know, let's see, here is, let's say this here is the x-axis, and we know that here between 0 and 1 somewhere is this number c. Okay, I want to find it. Now remember, the value of the function at 0 is negative. It was -1, so it's negative. And the value of the function at 1 is 2, so it was positive. Okay, so that's what tells me, that the function came from here to up here, and eventually somewhere it's gonna go through the x-axis, and that's the c that we want to figure out. Okay, it's our job to find this c with a 2 decimal place accuracy. Let's do that. Should use undo. Okay, so let's do that. So here is the strategy. We could do the following. I kind of mentioned once this procedure of divide and conquer, of splitting something two when you wanted to look for some items in an ordered list in a fast way. Well, we can use the same idea here, the bisection method. And what's the idea? Well, the idea is that I can split this in two. Okay, so I will be 1/2. And then I will ask, okay, what's the value of the function at 1/2? Okay, just plug in 1/2 and see what we get. I don't really want the value, but I want Well, I want the value because if I get 0, then we found the solution. Okay. Now, if I don't get 0, I will get a number that's either positive or negative. Let's see. If the number is positive, what does that mean? It means, notice that at 0, the function is negative. At 1/2 now is positive, so that means the c that I'm looking for is in this half. It's no longer in the second half of the interval. So now I focus on that half and I repeat the process. I do half again and so on and so forth until I find it. Okay. Now, similarly, if it's less than 0, again, that means that the c that I'm looking for, or at least one of the c's that I'm looking for, is going to be in the second half, because at 1/2 is negative. At 1, the function is positive, so the c is somewhere in here. Okay. And then, I keep doing half and so on and so forth. So that's one way of doing it. It's just that this way is a little bit slow. Like, we don't get close to, because, what if c is like very close to 1 or very close to 0? We don't get close to c very fast. We have to do this a lot of time to be able to find c. Even more if we want to get within 2 decimal places of accuracy. So I'm just going to use this idea a little bit more enlarged, because we're going to use the computer anyways. So why not? So what I'm going to do is, instead of splitting the interval in half, I'm going to split it in 10 pieces. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. I think I have 11, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So, okay, I will redraw up to here. And this is 1, and then remember, f of 1 is positive. So, and here we're going to have 0.1, 0.2, 0.3, and, and so on, 0.9. So, for example, and then what I'm going to do is I'm going to evaluate the function at all of these points. And we're going to see in one of these little intervals, we're going to have a change of sign. It goes from positive to negative. So that means our c is going to be inside that little interval. Okay, it's either one of the points, and then if it's one of these points, we found it. If not, it's inside that little interval where the function changes sign for the first time. And then we already got 1 decimal place of accuracy. Because, for example, let's say that it turns out that c is somewhere in here. Well, if that happens, that means that c is between 0.2 and 0.3. So that would tell me then that c is 0.2 something. I already got 1 decimal place of accuracy right there. Right? So now the idea is we're going to take that little interval from 0.2 to 0.3, divide it into 10 more pieces once again, and repeat the process. This is going to allow me to then get the second decimal place, and so on. Okay? So that's what I'm going to do. And of course, I'm going to do this with the computer. So let me turn over to Excel. Okay, so let me share the screen here. This other screen. And then I'm going to open up Excel. All right, let's make it big. Okay, so here we have Excel. Let me zoom this maybe to 200. Okay, so it should be big enough. Okay, so let's see, I'm gonna put my x's in here, and then I'm gonna put my y here, so my f of x. And initially, remember, I'm doing from 0 to 1. So 0, 1, oops, 0 to 1, and I want to split into 10 pieces. So 0, 0 0.1, 0 0.2, etc. Get the pattern. There it is. That's my first division of the interval. And now let's evaluate the function. So the function is x cubed plus 2 times x minus 1. Okay, so expected the value of the function at 0 is negative 1, and then drag and drop. The value of 1 is 2, as we knew. Now, looking at this list, center this, right? So looking at this list, we actually observe that right here, looking at the y values, we see the change of sign happening at that moment, right? So between zero point 0.4 and zero point 0.5, the function goes from, that's when the function goes from negative to positive, between zero point 0.4 and zero point 0.5. So that means that my C is actually here, okay? Between zero point 0.4 and zero point 0.5. So let me copy this and put it in here. Let's wait until this syncs. Okay, good. All right, so I have a picture. Then let's go back and repeat. Let me see if I want to make this bigger. Nah, that's okay. We'll be able to see it later nicely. Okay, so that was this means that C is between 0 0.4 and 0 0.5. Okay, so I already got one decimal place, 0 0.4 something. I want two decimal places, so let's repeat the same thing. Let me just leave it there. So X, or actually I'm gonna reuse it. So now this time that means I want to have 0 0.4 here, okay? And then I would like to end up with 0 0.5 here. So I have to split into 10 pieces again. So this would be 0 0.41, 0 0.42, etc. until I get to 0 0.5. So for 1, for 2, for 3, etc. Now let me remove this. Now we look at our new values, okay? And then we take a look and see where do we see our change in sign for the first time. And then we observe that this is happening right here. In other words, the C is between these two numbers. So our C is 0.45 something, okay? So we already got two decimal places right there. I'm gonna do it one more time since, it's really fast anyways here with the computer. I'm gonna do it one more time just to, if you wanted to round, but you would know, are we closer to 0.46 or are we closer to 0.45? Okay, so I'm going to do this one more time. Okay, sometimes it does not behave good. Okay, good. So let's do it one more time. So now I want to start here at 0.45. I guess 0.45, 0.45, and then I want to finish at 0.46. And then here will be 0. Remember, divide into 10 pieces that little interval again. So 0.451, 0.452, etc. So drag and drop now. Okay. Oops. Get rid of this. And make sure that the formula is there. And then we want to see where the first change of sign happens, and we notice that it happens right here. Okay. So the function changes sign between the first time that changes sign is between 0.453 and 0.454. Now we know, actually we know up to 3 decimal places is 0.453, etc. But if you want to round to 2 decimal places, it's really 0.45. Okay, so this now I'm satisfied. I know that even by with rounding to 2 decimal places, the answer will be 0.45 if we round. Okay. All right, so let me return to my other screen and then do the analysis. Oh, we did the analysis out loud. Just write down the conclusions. Okay, so using Excel, we did these computations. Okay, and then for the first iteration, so this is first we split the interval from 0 to 1 into 10 pieces. Let me, I guess, do a picture here. We split the interval from 0 to 1 into 10 pieces, and then this is where we saw the changing sign for the first time. So that means that C is going to be 0.4 something, okay, because it's between 0.4 and 0.5. Okay, let me actually say C is between 0.4 and 0.5, so C is 0.4 something. Now we do it again because that's not the accuracy that we want. And we do it again. Now remember, this is the interval between 0.4 and 0.5. We split it into 10 pieces and repeat the process, evaluate the function. Then we find the sign, the changing sign between 0.45 and 0.46, or C is between these two. So now updating the value to make it more accurate is 0.45, etc. So, up to 2 decimal places, you could say 0.45, but I want to make sure that if you were to round, is it really 0.45 or do we need to round up to 0.46? That's why I did a third iteration. Okay. So between 0.45, 0.46, and then it turns out that here is where we found the changing sign. So this is telling me then that C is really 0.453 and all stuff. So now we are confident that if we round to 2 decimal places, we certainly can round to 0.45. Okay, this is how, and you can get whatever accuracy you want, whatever desired accuracy you want. Just, keep on doing this until you're satisfied. You decide how many decimal places you want in practice. Okay. All right, so hopefully you understood this application or the intermediate value theorem, because it's very important. It actually gives you hope. It allows you to be able to solve, any equation really, at least to approximate the solution, as long as the function in question is continuous. Okay. So let's see. That was that example. We'll do one more, and then I will stop. Let me say show that the equation x plus e to the x equal 3 has a solution. Then let's approximate it to 1 decimal place. Let's do it to 1 decimal place. Let's do it quick. Okay, so now this is a little bit more interesting also, because this is no longer a polynomial equation. This is now polynomial plus an exponential. And here we are really out of luck if you want to solve this algebraically using your knowledge from college algebra and so on. We just don't have a tool to solve this. Okay, but nevertheless, we would like to see whether this has a solution or not, and if it has, we want to be able to say something about it, at least approximate it as much as we want. Okay, that's the point here. All right, by the way, I want you to see that in this case, because these are easy functions that we can graph, we can actually see that there will be a solution to find. And this solution is going to give us also a hint, because notice that in this problem, I didn't give you an interval. Okay, so in the previous problem, we're given the function and we're given an interval, and our job was just to make sure that inside this interval there was a solution. But we're already given the interval, so we just plug in the endpoints, and by continuity, we can use intermediate value theorem. But here we are not given the interval, and we need the interval if we want to use it. Okay, the intermediate value theorem. So you either guess the interval by starting picking reasonable points until you find something that give you what you're looking for, or you analyze the equation a little bit more and do be a little bit more intelligent about it. And that's what I'm about to do. So solution. So I want to find an interval, but I want to go for sure, okay? And here is what's going to happen. So we want to solve x plus e to the x equal 3, okay? But I'm going to transform this equation a little bit, okay? Notice that this is the same thing as this equation is equivalent to the equation e to the x equals negative x plus 3. Just move the x to the right hand side. So to solve the original equation is equivalent to solving this new equation that I draw here. Why did I draw this equation? Because now I can analyze what's happening here geometrically. Because basically, the equation on the left is exponential function e to the x. We all know how it looks. It goes through 1, and it's an exponential function. So this is this graph. And the equation of the right is a line. Once again, we know how to graph it. It's a line with negative slope, moreover. So the y-intercept is 3, and then the x-intercept is 3. So 1, 2, 3. And then it's a line with negative slope. Let's put it here. So it's a line with negative slope. This is the line y equals negative x plus 3. And then to find a solution to the equation is to ask when are these two functions equals. In terms of the graph is when do these two functions meet, if they meet at all, okay? And we can actually see that there is a solution, okay, right here. Whatever this x is, I mean, I don't know if, let me just do this, because I don't want to say whether it's bigger than 1 or not, because I don't know. But whatever this x is, what I can say for sure is that this c is the one that we are after, okay? Whatever that is, that's the one that we're after. But now by looking at the picture, we can immediately say, oh, but I know this is between 0 and 3 because the picture is telling me this, okay? So we have something to begin. We have something to start from, okay? So first of all, now we can see that this guy right here is a solution that we are after, okay? And, here we geometrically, we actually we show that there is a solution. So we're basically done. But now, I'm going to use intermediate value theorem just to confirm this. I mean, we already have it there, but also as practice. But where the intermediate value theorem really is going to be very helpful is to help us find this solution. If it's something more complicated that you cannot draw, that you cannot graph, like we did here, what you need to do is start plugging in numbers until you find something that works for you. Okay? Now, I know that this is telling me then that the C, it will be between 0 and 3. Okay, so from now on, I'm going to be focusing on that interval. But first, let me show you how we can use the intermediate value theorem. Because we have an equation, we need a function. The question is, what function do we use? Okay, so note x plus e to the x equals 3, as I said. And instead of looking at this, what I'm going to do is I'm going to look at the function. I'm going to move everything to the left hand side and set it equal to 0. So once again, this is equivalent to saying x plus e to the x minus 3 equals 0. And so this would be my function f of x. Okay, so let f of x be equal to x plus e to the x minus 3. Okay, this is certainly continuous because it's a polynomial plus an exponential, and sum of continuous is continuous. So it's continuous on the entire real line. In particular, it's continuous on the closed interval from 0 to 3. Okay, so it's continuous on the closed interval from 0 to 3. Why 0 to 3? Because that's the one that I found on the top. Okay, you could try to see if 1, it looks like this is probably close to 1. So what happens at 1? And then you can do that. But I'm just going to do 0 to 3 because that's the one that the picture gave me for sure. But you could use 1. Okay, from 0 to 1, because let's see, if we plug in 0 into the function, what do we get? We're gonna get -2. And if we plug in 1, we get e minus 2, and e minus 2 is positive because e is 2 point something, right? So 0 to 1 does the job. but that's fine. From 0 to 3 is also okay. So this function continues on 0 to 3. Also, the value of the function at 0 equals, you know, 0 plus 1 minus 3, which is negative 2. So it's a negative number. The value of the function at 3 is going to be equal to 3 plus e to a 3 minus 3. So that's e to a 3, which is certainly positive. So that means because the function is continuous on the closed interval 0, 3 and changes sign, then that function has to have a 0. So it has a solution. So by the intermediate value theorem, the function f of x has a 0 in the interval 0, 3. We know actually it's between in the interval 0, 1 because if you plug in 1, you also get positive. But that's going to come now when we start computing. It has a 0 in the interval 0, 3. So the equation x plus e to the x equal to 3 has a solution that is between 0 and 3. Okay, and this actually answers the question, right? The question was to show that the equation has a solution. Okay, we just show it. We actually show it in two ways. We did it graphically, but what if the graphical approach doesn't work because it's too complicated to actually graph it? Well, just send everything to one side, set it equal to 0. The thing is that then you wouldn't have your interval. We got the interval from the graph. If you don't have the interval, then you have to start trying. Like you look at your expression and you say, okay, I'm gonna plug in 0. Usually 0 is nice, so plug it in, see what you get. And then try to find another point that will give you the opposite sign. And then you will have your interval because those will be the endpoints of your interval. Okay? All right. So now we find the solution. Now we find the solutions. The solution to one decimal place. Okay, and I'm gonna turn to once again to Excel, and let's just to finish this example. Okay, so let's see. This time our interval was from 0 to 3. Okay, so let's see if I want it to be ultra super picky. Okay, that's fine. I'm just gonna yeah, it should divide into 30 pieces because I have 3 unit intervals, 0 to 1, but that's okay. Let's see. From 0 to 3. Okay, so here's what I'm going to do. First, I want to know, let's say that you didn't plug in 1, okay? So I want to know, okay, it's between 0 and 3, but is it between 0 and 1, between 1 and 2, or between 2 and 3? That's the first thing that I want to know. I mean, we already know, by the way, but let's first get that out of the way. So this is how you would do it, you know, if you don't want to compute and you already have your computer with you, you know, just go ahead and try this on your own. It's clear content. Okay, let me put this. Okay, so my function is, what was the function? The function is x plus e, that's the exponential function, e to the x minus 3. Remember, that's the function f. We needed to modify the equation. Okay. All right. And then, you know, as expected, yes, at 3 is positive, but, you know, it's a big positive. So we know it's going to be positive way before that. And, you know, and also you can see it from the picture. Let's see. You see, 3 is all the way over here. We know that our C, look where the intersection happens. So our C is really, you know, closer to 0 than to 3, as the picture suggests. Now the truth is revealed. Basically, you know, is between 0 and 1. It's true it's between 0 and 3, but now we are closer to the truth. It's between 0 and 1. So as a first little clue, let's put it there. So, and this way we know now we focus between 0 and 1. We don't have to worry about what happens around 3. But it's really between 0 and 1. Okay, let's go now. So put 0 here, and then we do 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 here. And so I split that interval into 10 pieces, as we did before. Okay, so 0.1, 0.2. Okay, so the interval from 0 to 1 split into 10 pieces, and then just evaluate the function at all of those pieces. So taking a look at the behavior of the values, then we see that the first time that the function changes from negative to positive is right here. Okay, so we have that our solution is actually between 0.7 and 0.8. So C is 0.7 something. Okay, here. Okay, it's 0.7 something. And since I wanted one decimal place, but let's do it with rounding. So I'm gonna do one more iteration. So here is 0.7. I want to end up at 0.8 and split that little interval into 10 pieces. So 0.71, 0.72, and so on. Oops, no. Okay. Get rid of this one. Now, taking a quick look. Oh, look at that. So it's right at the very end is when we see yeah. So right at the very end, that's when we see the values changing. Okay. So it's 7.79 something. It's between 0.79 and 0.8. So if you're gonna round, it actually rounds to 0.8, right? Not 0.7. So that's why it's good to do one extra iteration. Okay. So since I'm here, before I go now and write the final comments, let's actually verify this with Wolfram alpha. Okay, so our conclusion is the solution should be 0.79 all stuff. Rounding to one decimal place, it would be 0.8. Okay, for that equation. So let's see what Wolfram alpha has to say about this. Okay, so Wolfram alpha, and then I'm just gonna ask you to solve the original equation, which is x plus e to the x equals 3. But that's equivalent to ours. Okay, so here you can see the solution, right? This is the approximation to the solution, 0.79, and then here we have a couple more decimal places. But we only did it up to here, so we knew this already, and it rounds to 0.8. So we're good, as you can see. And then let's actually, since we're here, let's verify the other one. So that was, what was the polynomial? X cubed plus 2x minus 1. So solve x cubed plus 2x minus 1 equals 0. Okay, I want the approximate form. Okay, and here we can see, because it's a degree 3 polynomial, that's why you see 3 solutions. One is a real solution, as expected, and the other 2 happen to be imaginary. And now we can see it's 0.453 all stuff, and that's exactly what we came up with. You see, 0.453 all the stuff, so rounds to 0.45. Okay, so intermediate value theorem is very helpful. All right, so let me just do the final remarks in here. Okay, so this problem then, this then tells us that the solution C is between 0 and 1. This one tells us that C is 0.7 something. And then this one here tells us that C is actually 0.79 something. So we want it to one decimal place. The answer is the solution is 0.79 all the stuff, which approximates to 0.8. Okay. All right, guys. So with this, we are done with the discussion about continuity. So this is a stopping point for the exam. So you will have up to the application of this theorem, intermediate value theorem. Okay. Of course, when I ask you a problem, I'm not gonna ask you to actually do this because you will need a computer and you're gonna do the exam in the class, right? You will need a computer or a calculator, but you're gonna be plugging a lot of numbers and you're gonna waste too much time. But the question would be to argue that a given equation has a solution, and basically what you will need to do is verify that the conditions of the intermediate value theorem are satisfied. In other words, if you look at question number 2, you will have to do up to this, right? Up to this point. Just saying, verifying that the conditions, the function is continuous on the interval. You will have to come up with the interval, verify the function is continuous, it changes sign, and therefore it will have a zero in that interval by the intermediate value theorem. Okay. But the second step, the second part, which is to actually approximate the solution, I'm not gonna ask you because you will need a computer or a calculator, and you won't have that. It will take you some time to do in the exam. I don't want you to go through that. Okay. But make sure that you understand how to do it, because if you're gonna be engineers, most of you, this is the practical application that you can use for that theorem, for this theorem. Okay, guys. So this is enough. Once again, the exam stops here. We're gonna have the exam next week on Wednesday, and then for next Friday, when I do the next video, I will be introducing to you the next chapter, which is differentiation.